Hi, my name is Peter Smiley, and I worked with Alexander Cito on a project using satellite imagery for classification of urban and rural areas. So, collecting information about the people within a country is a huge deal for the United States and many countries around the world. Um, Understanding demographic data is useful for distributing funds and make policy decisions that have impact on these people. The cost to collect this information scales in parallel with the population size of these countries. So as a country's population grows, the cost to collect this information will grow as well. Modern technology should be targeted towards alleviating these costs. However, the method to collect demographic data is still through funding large-scale surveys. A notable example of this is the United States Census. Due to the public availability of satellite image data and the ease of access to these data sets, we are looking to see if we can get good estimates of the demographic data based on satellite images. This will hopefully provide a cheap and easy path to collecting key demographic data on a large scale.
We're not the first to use satellite imagery as a predictor variable in a machine learning framework. There exist many use cases for both regression and classification utilizing remote sensing data. The most obvious use case is predicting geographic features. Like in one paper, the authors propose methods to extract Arctic melt ponds, critical features of the Arctic ecosystem for understanding how an ecosystem will operate. This is shown in the top right image. However, other use cases include predicting population and demographic statistics, such as a paper where the authors use convolutional neural networks to predict population numbers comparable to the census values. The bottom right image shows the feature activations from their network.
After finding many machine learning papers related to satellite imagery, we found one by Google researchers where they set out to find baselines for fine-tuning neural networks on 5 popular classification datasets with satellite images. They evaluated their performance with respect to both their upstream and downstream performance, and the data and pre-trained models from their experiments were published to TensorFlow Hub and TensorFlow datasets, meaning we ourselves could access and experiment with the models they used. Specifically in their experiment, they utilized pre-trained ResNet 50 v2 architectures with single classification layers with the softmax activation function as the base model for each of their experiments. In the paper, the authors compare models pre-trained on ImageNet to ones pre-trained on both ImageNet and one of the tasks from the 5 datasets, evaluating the model's performance in fine-tuning on one of the remaining 4 datasets, meaning they're checking both the upstream and downstream performance for 2 different datasets in one experiment. The results of this can be seen in the table at the bottom of this slide, where the rows represent performance for a model pre-trained on that dataset, and the columns represent the performance on that dataset as a downstream task. Clearly from this table, by the bold numbers, you can see that models that were pre-trained on the ResISC 45 dataset did the best across all other tasks. And so, we, in our own methodology, decided to pre-train a model on the ResISC 45 dataset and fine-tune it to our own custom task. The ResISC 45 dataset is a dataset of 31,500 images of RGB channels split into 45 classes, each containing 700 256 by 256 pixel images. As said before, it was the best performing dataset from the Google researchers' experiments, and the dataset itself has varying spatial resolution and high in-class diversity as well as out-of-class similarity, as the authors of the dataset specifically designed it to be a challenging task for deep neural networks. So as for our final methodology for our experiments, the first step was to collect and pre-process data relevant to our urban-rural classification task. The second step was to train a base model on the ResISC 45 task using a similar method to the authors from Google. And then the final bit of our experiment would be to compare the performance of the pre-trained model on ResISC 45 to a plain pre-trained model on ImageNet on our binary classification task. So getting the satellite imagery data that was labeled itself was a problem. There was no existing data sets out there that were labeled at the coordinate level, so we couldn't really find any way to associate it with existing demographic data, so we set out to go and get that data ourselves. So part of this was making a script that randomly generated US coordinates, downloaded all the images corresponding to those coordinates, and filtering out empty images and images of just water. On the left, you can see examples of the images in our data set. and also the labels. And so when it came to finding the labels for our problem, we originally were going to use population density and treat this as a regression problem. However, we struggled to find any significant results in modeling that function, so we turned to a binary classification problem with urban and rural areas. Specifically, we used the National Center for Health Statistics urban-rural classification scheme, utilizing classes 1 and 2, large central metro and large fringe metro, as the urban class, and class 6, non-metro, non-core counties as the rural class. Examples of the overall distribution of our country's counties can be seen in the top right, and in the bottom right you can see the distribution of classes in our own custom data set. When it came to training the base model on the ResX 45 dataset, training was very straightforward. We easily achieved 90% validation set accuracy using the parameters from the paper by the Google researchers. For the primary experiment, we found negligible difference between training the model trained on only the ImageNet dataset versus the one that we had pre-trained on the ResX 45 dataset as well, with both of them converging to about 80% categorical accuracy, and we attribute this to issues within our data as well. Discuss this later, but we were still able to make use of the feature activation outputs.
So here's an example image from our dataset and the corresponding feature activations from the model on the ResX and ImageNet dataset. So even though we have gotten subpar results from the model is still able to pick up on what is relevant for our classification task. So pay special attention to the second row on the feature activations. You can see that the model is able to pick up the difference between the farmland and the buildings in the image, as well as other indicators such as like the road. So on the left side of these images, you can see the farmland is lit up, and the roads are also displayed. There were limitations in our study, such as the lack of a comprehensive image filter. So in the resulting dataset, there were still water images and useless images left in, like blank images. There was a lack of data augmentation and balance across classes, and satellite images were not at the county level, while the urban and rural labels were. This could create extreme bias in the results, as well as the essential task we have the model learn.
As for conclusions from our experiments, we know that the data collection requires great modification, whether that includes data augmentation, better filtering, or rebalancing of the dataset's classes. We need to improve the dataset in one way or another because we don't know how to properly evaluate on the task. Furthermore, analysis of the examples which will maximize the loss and the feature activation outputs can guide us into what examples and what features we need to add to the dataset such that the model can learn to differentiate the classes better. Overall, we provided a proof of concept for use of pre-trained models to predict the population statistics, as we used the ResX 45 dataset to pre-train our base ResNet 50 on satellite imagery, so it would have a better sense and a better initial filters to pick up the features that are relevant to any sort of classification in satellite imagery. Lastly, this sets the stage for potential cost-saving survey replacement using regression or classification on satellite imagery data.